So what we're doing today is volume by slicing. The idea is we take an object and slice it up into an infinite number of slices and add those slices together. And so what we're doing is, and there's a nice video to watch, but pretty much the bread demonstration, it does the same thing. If you want to watch it, it'll be on the notes. You can do it. It's a nice little demo, but it's really not that fantastic. So if the cross-section has an area A of X, the cross-section, the area, the surface area of my cross-section as I slice it up, has that cross-sectional area, then the volume is that cross-sectional area. It's the integral of that cross-sectional area from A to B. But remember, what is dx? Dx is the change in x. This is the change in x. So this is the cross-sectional area times, that's essentially the height or the depth of each slice. The cross-sectional area times the width of each slice. That's what dx is. The change in x, the distance in x, is that. And by using an integral, we use an infinitely thin slice. We're adding together an infinite number of very thin slices. This is a volume. A of x dx is the volume of one slice. Doing the integral is adding up an infinite number of those slices to get the volume. That's the idea behind it. So this is really the cross-sectional area times the depth of each slice that we have. But by integrating, we can just do a tremendous number of them. Okay, does that make sense? So that's kind of what we're doing. We're slicing it up. The key to doing it by slicing is each cross-sectional area has to be the same volume. If it's not the same volume, it doesn't work. Okay, or I mean, same cross-sectional area, you can't do the volume. So I've got a couple of examples here. First one, the mathematician's paperweight problem. Obviously, this is a classic problem because it's a mathematician's paperweight. We all have the same kind of paperweight. Didn't you know that? I have one of these at home. Okay. So a mathematician has a paperweight made so that its base is the shape of the region between the x-axis and one arc of the curve of y equals 2 sine x. So this is the x-axis, y equals 2 sine x. Each cross-section perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. Find the volume of the paperweight. Okay, each cross-sectional area, each slice perpendicular to the x-axis. So just like I sliced up the bread, I have a bunch of perpendicular slices. I'm slicing it this way. Each one of these slices, if I were to pull it out, is a semicircle. So what's my cross-sectional area? It's a semicircle. Okay? And the diameter of that semicircle is the distance between the x-axis and the curve 2 sine x. So the diameter is 2 sine x. That's what that problem tells me. Okay, does that make sense? Do you see where I'm getting my cross-sectional area? Because that's what you have to be able to identify. This is the most difficult thing, is finding the formula for the area. And if you do what I did here and say, okay, I'm going to draw little slices, because that's how I'm cutting it up, pull one of those slices out, and what is the equation for this cross-sectional area? What is the equation for one of those cross-sections? Well, the information given, the diameter of that semicircle is 2 sine x. So I have to just figure out what's the area of that semicircle. Well, the formula for a semicircle is 1/2 pi r squared, right? Because pi r squared is a circle, so half of that is a semicircle. Right? Okay. Do I have my radius? Can I find my radius? Yeah, because my diameter is 2 sine x, so what's my radius? Sine x. So that's my diameter. This is my radius, would be sine x. So that means my area would be 1/2 pi sine x squared. So my integral to solve this problem, pi over 2 sine squared x dx. Okay. Pi over 2 sine squared x, that's the area of my semicircle. 1/2 times pi over 2, r squared. This is the area. So it's the integral of the area dx. Now I got to figure out my balance. Well, where is 2 sine x and 0? Where is it 0? It's 0 at 0, right? Because the sine of 0 is 0. And then the sine of the next place where it happens is at pi. So it goes from 0 to pi because those are the points of intersection. The edge of the loaf of bread is as you work. Okay. Does that make sense? You understand where I'm getting my information from? Because I'm going to tell you, that's what you need to have, or I should say that's 90% of what you need to have on your test. It's 90% of what you need to have to solve this problem is the actual equation. That's the part I'm looking for. Now, one of the things you can do is if I have a constant, I can pull that constant out front. Pi over 2 times the integral of 0 to pi of sine squared x dx. And I can do the integral of sine squared x dx. And you have to do this one on your calculator. You cannot, there is no antiderivative of sine squared. There is none. Okay? If it were the old days, it would be something like the trapezoid rule or Simpson's rule, which is even more complicated, but much more accurate, and would have to be like 15 or 20 or something like that to make it good. But you have graphing calculators that will do this for you. If this was a test question, I'm looking for that. And I'm looking for this. I think it's 967. It might be 467. That's hard to read on handwriting sometimes. Well, that's what you get. But if you have a constant, you can pull that constant out. 2 reasons to do that, or actually, yeah, 2 reasons. If you're doing it by hand, pull that constant out front, and you can take the antiderivative of what's inside, no problem. Makes it a little easier. If you have pi over 2 times x cubed, pull the pi over 2 out, then deal with the x cubed on its own and do that integral on its own, then take that answer times pi over 2. If you're typing it in the calculator, you can type all of this in your calculator, or you could type just this part into the calculator to do your integral. It's a little easier, a little less to do, and then take what you get for this, multiply it times pi over 2. It's the same thing. Pulling that constant out is the same thing. And when we start going over AP practice questions, they will give 1 point for, they will give a point for having this. A, B, and that constant of integration. We'll see more of that when we come up to the next section. Yeah. So pulling that out, and it doesn't matter whether that's in or out, you'll get the same answer either way. Okay? You with me so far? Who? The mathematician's paperweight problem. Again, mathematician has paperweight made so that its base is the shape of the region between the x-axis and one arch on the curve y equals 2 sine x. Ooh, same thing. Each cross-section cut perpendicular to the x-axis, same slicing action, is a right triangle. Ooh, not a semicircle. A right triangle whose base runs from the x-axis to the curve and whose height is twice the base. Find the volume of the paperweight. So almost everything is exactly the same. We still go from 0 to pi. And we're still slicing it the same way, perpendicular to the x-axis, right? But our slices are not the same shape. These slices are, right, triangles, whose base is the distance between the two curves, 2 sine x, and whose height is twice that. So if this is 2 sine x, what's the height going to be? 4 sine x. Okay. The key to doing these problems, draw the freaking diagram of your cross section and label it. It makes life so much easier when you do that. You draw, ooh, I have a triangle. What's the area of my triangle? It's 1/2 base times height. I've had students argue with me that no, it's not 1/2 base times height. It's base times height divided by 2. I know. It kills me. When I'm teaching geometry, I've had kids, no, Mr. Orris, that's wrong. What do you mean that's wrong? And yes, they've argued with me over that one. I'm like, really? Well, my elementary school teacher, who do you think that's for? Me or them? It's the same thing. Okay, so you take the equation and you figure it out. Plug in the base and the height. And I always start out just plugging it in as it stands. I don't simplify anything in my head. I write it down. 1/2 times base times the height. I want to clean it up before I put it in my integral. But I can want to do that now. If you wrote an integral, if you wrote your integral as this, from 0 to pi of that dx, that's good, because that's perfectly accurate. That's exactly what it is. Is it nicer to have it as the integral from 0 to pi of 4 sine squared x dx? Yeah, it is. It's a little nicer and cleaner. But is that accurate? Yes, it's perfectly accurate. This is cleaner, prettier. That's all this is. It's just prettier. Okay. That's the only difference between those two. And perfectly honest, if this was an AP question, that would be a perfectly fine answer, and they would give that to you. This would be what they would have as their answer on their key, but they would accept that. Okay. And then you would have to work that onto your calculator, which I did ahead of time because I'm smart that way. And I knew the questions before the test. 6.283. The whole key to this, the most difficult part of these questions is coming up with the correct formula for the cross section. That is by far and away the most difficult part. That's where everybody trips up. And what really makes the difference is drawing the diagram. Copy this onto your paper. Do the cross-sectional slices. Pull out what does one cross-sectional slice look like. Label it with the information given. And then come up with the area formula for that cross-sectional slice. That's what you can do. It's not difficult if you do this. Okay? Sketch the thing. Draw the cross lines in it for what you would have. Okay? Questions? Okay. Your turn. So when you're doing this, you have two problems. The first problem, cross-section perpendicular to the y-axis. So the first one, your slices are going this way, which means that you need to do it dy. So instead of y equals x squared, you have x equals the square root of y. Instead of y equals x cubed, you have x equals the cube root of y. Your bounds are from 0, 0 to 1, 1. You've got to be able to figure out where they cross each other. Just set x squared equal to y squared. If you don't have the points in the graph, solve for that. So first one, my cross-sectional area, it's a square. Okay, and it's the distance of the upper curve minus the lower curve. The farthest right curve minus the farthest left curve. So this is the upper curve when you're doing dy is the one that has the highest x values, which is the cube root 1 when I'm less than 1. So the side length is the cube root of y minus the square root of y, which means the area of that is the cube root of y minus the square root of y squared. So my volume for this one is the integral from 0 to 1 of the cube root of y minus the square root of y, quantity squared, dy, and you get, and you get 0.00909. Second one, your cross-sectional slices are perpendicular to the x-axis. Okay. Your upper curve is x squared, your lower curve is y squared. Oh, sorry, y cubed. So I have a square, x squared minus x cubed. The area of this is x squared minus x cubed, quantity squared. So my volume is the integral from 0 to 1 of x squared minus x cubed, quantity squared dx, or 0.0095. Nearly identical. But not quite. And then you would have to give an explanation. Which direction your perpendicular slices are determines whether you do dy or dx. I have to do dy on the first one, dx on the second one. The distance between the two curves, that's the distance of my side length. You will have triangles, you will have squares, you will have rectangles, you will have semicircles. You might have full circles. Guys, your book often has diagrams. Please take the time to copy them down on your homework. Draw them, label them, write on them. Don't write in the textbook. Write on your homework paper. It really makes a difference. Now, I will help you with one of the problems or one of the types of problems you will have on your homework. It will give you the cross section is a circle. If it is a circle of radius 1, x squared plus y squared equals 1. Whatever the radius is, that's what it's equal to that number squared. The radius 1, it's equal to 1. Okay. Well, I want to find, let's say I have a cross section with semicircles that run the whole length. That whole length cannot be used doing that. You can't use the equation of the circle as it stands. What you need to do is you need to figure out what this one here is. And conversely, what this equation here is. And that will give you what you need. So what you have to do is you've got to take x squared plus y squared, rearrange it to get y equals. It's not that hard, is it? Subtract x squared from both sides. Take the square root. plus or minus the square root of 1 minus x squared. Plus is the upper half, minus is the lower half. Do I really need to have this whole length here? Not necessarily. I could just use this distance here and double it for whatever I have for, let's say, a diameter. If I have a diameter's half. Radius is half that distance. It's the same either direction. You're going to want to know this for your homework problems. Read the questions carefully. Draw a diagram of the cross-section. If it's a semicircle, that's one thing. If it's a triangle, read carefully what the base of the triangle is and how you're going to find your height or the other lengths involved. Okay? I think there's one of them, I could be wrong, that you have a cross-sectional slice is a square with the diagonal as the length. The diagonal of the square, not the side length of the square, the diagonal of the square is that length. You still have to figure out the formula for the area based on that. So you're going to draw on your geometry skills on this one. Okay. Questions? Awesome sauce.